The paper introduces ScholarChemQA, a large-scale question-answering QA dataset constructed from chemical papers, aiming to bridge the gap in academic chemistry research. The dataset consists of 40,000 instances, with 1,050 answer labels annotated for training, validation, and testing. The authors propose a QAMatch model, specifically designed to effectively answer chemical questions by fully leveraging the collected data. To address the issue of imbalanced label distribution, the instance-wise loss is reweighted based on the inverse frequency of each class, ensuring minority classes are not dominated by majority ones during optimization. The unlabeled data is utilized to enrich the learning process, generating a variety of augmentations based on a SoftMix operation and ensuring their predictions align with the same target, i.e., pseudo-labels. The QAMatch model significantly outperforms recent similar-scale baselines and large language models, LLMs, not only on the ScholarChemQA dataset but also on 4 benchmark datasets. The ScholarChemQA dataset is a comprehensive collection of chemical question-answering tasks, comprising 54% of questions that require chemical knowledge for answering. The dataset covers a wide range of topics, including biochemistry, theoretical chemistry, catalysis, environmental chemistry, and material chemistry. The questions are categorized into 3 main aspects: chemical interaction, chemical theory, and chemical attributes, with the majority falling under the category of chemical attributes. The QAMatch model is designed to tackle the task of chemical QA, which is formulated as a C-class classification problem in a semi-supervised learning setting. The model takes into account both labeled and unlabeled instances, with the objective of minimizing the supervised cross-entropy loss and unsupervised consistency loss. To address the imbalance problem in the class distribution, the authors implement a strategy of label rebalance during the supervised training phase and pseudo-label calibration during the semi-supervised learning process. The research paper also discusses a novel approach to semi-supervised learning, focusing on improving the accuracy and robustness of text classification models. The QAMatch model leverages both labeled and unlabeled data, utilizing a pseudo-label calibration process and a SoftMix augmentation operation. The SoftMix operation enhances diversity and robustness by interpolating in hidden layers, which is particularly effective in the context of question and answer pairs. The model is trained using a combination of supervised and unsupervised losses, with the goal of improving the model's ability to learn from unlabeled data. The paper presents experimental results on various datasets, including the AG News, Yahoo Answers, Yelp 5, and Amazon 5 datasets, demonstrating the QAMatch model's consistent outperformance over other semi-supervised and supervised baselines. QAMatch, a novel semi-supervised learning approach, leverages both supervised and unsupervised data to improve performance on imbalanced datasets. The model's effectiveness is demonstrated through evaluations on various benchmark datasets, showcasing its resilience across diverse data distributions. Comparative analysis with large language models, such as Llama 270B, GPT 3.5, and GPT-4, highlights the limitations of these models in chemical question-answering tasks. Tables 3 and 4 illustrate QAMatch's superior performance in handling imbalanced datasets, outperforming baseline models like FreeMatch and BioBERT. The model's success is attributed to its ability to effectively utilize both supervised and unsupervised data. An ablation study, presented in Table 5, underscores the importance of class balancing and augmenting diversity through the SoftMix component. QAMatch surpasses large language models on the ScholarChemQA dataset, likely due to its explicit training on the chemical corpus and enrichment with corresponding knowledge. A case study highlights the inconsistent reasoning process of large language models, emphasizing the need for strengthening domain-specific scientific knowledge in chemical QA tasks. The proposed class-balanced term, 1 minus beta ny, improves the original loss, with larger beta values yielding more significant performance gains. Pseudo-label calibration is demonstrated through histogram distribution and KL divergence analysis, showing predicted labels closely resemble ground truth labels. The SoftMix operation generates more diverse and informative representations, outperforming the remix operation in latent space. QAMatch outperforms the second-best model on the minority class, with a margin of 1.39. Confusion matrices visualize the model's superior performance, with a more balanced class distribution and fewer misclassifications. The utilization of unlabeled data is analyzed, with the accuracy curve of pseudo-labels highlighting the model's superior learning capability. An ablation study reveals the significance of class balancing, pseudo-label rebalancing, and SoftMix operation in achieving improved performance. Here is a combined summary of the 4 pages. The presented research paper comprises a comprehensive reference list, spanning machine learning, artificial intelligence, and computer science. The references delve into conversational question answering, exploring open retrieval methods, non-factoid question answering taxonomy, and biomedical research question answering datasets. They also investigate learning deep representations for imbalanced classification, question-oriented feature attention, and user profiling for question answering communities. Semi-supervised learning techniques are also discussed, including active learning for class imbalance problems, distributional random oversampling, and label distribution-aware margin loss. The references further cover Gaussian processes for rumor stance classification, latent discriminative models for social emotion detection, and equalization loss for long-tailed object recognition. The applications of large language models in biomedicine and health are examined, including opportunities and challenges for ChatGPT and large language models. Their ability to understand chemistry and perform tasks such as text-to-SQL is also explored. Techniques for improving machine learning model robustness are presented, including manifold mix-up, visualizing and understanding convolutional networks, and fix-match. Character-level convolutional networks for text classification and product bundle identification using semi-supervised learning are also discussed. Overall, the references provide a comprehensive overview of the state-of-the-art in machine learning, artificial intelligence, and computer science, highlighting various techniques, applications, and challenges in these fields.